Swayam Prabha. Digital India. Educated India.
So welcome back. So we were going through the energy and energy analysis. This is the third part of the module. So until now we have covered the concept of energy and energy transformation, and particularly internal energy and different forms of internal energy, and the work and heat which is recognized only at the boundary of the system. Now we will go in details of the first law of thermodynamics. Okay, so what it says that the first law of thermodynamics, that the energy cannot be created or destroyed, it can only change its form. So we have already given this example of rock falling from a cliff, where the potential energy of the rock gets converted into the kinetic energy. Okay. Now it depends on whether your system is isolated or whether the heat can be supplied or not. Depending on that, the change of energy can be calculated. So for example, you take a case of potato which you put it in the oven. Now potato does have its internal energy, but once you transfer heat in the oven, such as for example this value which is given 5 kilojoule, then the thermal energy of the potato is increased to the same amount, assuming that there is no loss in the energy. So this dashed line represents the system, so this becomes the system, and you are getting Q in from the surrounding or from the device which is oven in this case. If you take a system such that no heat can be transferred from the system to the surrounding or surrounding to the system, and if there is any change in energy, it has to be due to the net work done on the system or by the system. So that's another way of stating the first law, that change in the total energy during an adiabatic process where Q is equal to 0 must be equal to the net work done. Now let us take a couple of more examples. Okay, so this is an example here. Again, this could be a reactor, for example, where or container. Okay, anything which you can consider this. The dashed line again represent the system. So what is being given here is there is a heat provided to the system which is given as 15 kilojoule. There is a heat loss which is transferred to the surrounding, which is a 3 kilojoule. Thus your delta E, which is a net change in the energy, is simply the Q net, which is nothing but 15 Q in minus Q out. Okay. Now there is no work done in the system because work interaction is not given. So in the absence of any work interaction, the energy change is simply equal to the net heat transfer. Now you can consider a case where the system itself is adiabatic, meaning that heat transfer cannot be possible. So the only possibility to change the energy of the system is by doing a work. Now, work can be done either through electrical mean, through mechanical mean. So that's some examples, two examples we are going to consider. This is an example where the electrical work through battery is done on the system. So here you have system is adiabatic, which means Q is equal to 0, and the work in is 5 kilojoules, and if you do the energy balance, simply find out that the energy change of the system should be equal to W in. So that is 5 kilojoule. We can take another case, and in this case the work done is through shaft. So that is the work shaft. This is a representation of shaft. In is 8 kilojoule. Okay, thus your delta E is nothing but shaft work shaft in. Okay, so the work done on an adiabatic system is equal to the increase in the energy of the system, and for the case of the work done on an adiabatic system, which is electrical one, is also equal to the increase in the energy of the system. So we can write a very formal definition of the first law, okay, and that is how we are going to go about it in this course. So here is the total energy entering the system minus total energy leaving the system, and that should be change in the total energy of the system. So is E in minus E out and delta E system. So we will talk in more detail what is E in, what are the components which constitute energy in, and what about delta E system, what is the energy of the system. So this is something which we will describe more in detail. So you can use this expression to find out delta E of the system for the case of adiabatic system where the Q in or Q out is 0 and the change in energy here delta E of system should be E in. In this case, what is E in? There is a piston which is moving, the boundary is movable. So there is a boundary work which is done which is equal to 10 kilojoules. So E in is 10 kilojoules minus E out, there is no E out, so E out is 0. So delta E system should be equal to 10 kilojoules and that is what it is. So you are simply applying energy balance based on this expression. You can do the same thing now in a little more complicated where the work is also included. So here you have a shaft in, work due to shaft in means you are doing a work on the system, and then you have a Q in as well as Q out. Now what is the delta E system, change in the system? So it should be delta E system should be E in is your Q in plus W shaft in minus E out, in this case E out is Q out. So that makes your answer is 15 plus 6 okay, kilojoules minus 3 kilojoules, okay, that should be your 18 kilojoules. Now we will little bit talk about the E of the system. Now energy of the system is a point function. So essentially it does not matter how it was achieved, the state was achieved, you simply it is a difference between the final state and the initial state, that would be the change in the energy of the system. So that is something we are emphasizing again. So this and this is fixed once you have a state fixed, once you know exactly the state. But this consists of many components. So this consists of your internal energy, the potential energy and kinetic energy. If magnetic and other components like surface tensions components are missing or absent. So E final plus minus E initial can be written as E2 minus E1. In other words, you can also write delta E of the system as simply the change in different components of the energy. So this will be the change in the internal energy, okay, that means this will be U2 minus U1, and similarly for delta KE and delta PE. So the other component we are assuming that there is no magnetic effect, there is no electric effect, there is no surface tension effect, okay, because the gravity is considered as a part of potential energy as well. So you can write this expression in more detail. Delta U is nothing but mass multiplied by specific internal energy. So that means this is per kg form, and this delta K is given in terms of the velocity, P is given, okay. Now in case of a stationary system, so you have Z1s and Z2s are fixed, V1 and V2s are fixed, that means that they are also equivalent, same, which leads to your zero potential energy difference, zero kinetic energy difference, and thus your total energy change of the system should be same as that of the internal energy. So that is something which is obvious based on this expression. Now how do you achieve these changes? Okay, we talked about the change of the system, okay, but how do you achieve it? There are three ways to change the energy of the system, okay. Either you provide heat, or you take out the heat from the system, or you do a work on the system, or you make use of the flow, mass flow and mass out, okay. There are three ways to do that, and that is why we are going to use this control volume showing this open system as an example. So as I said, energy can be transferred to or from a system in three forms: heat transfer, work transfer, mass flow. If you close the system, okay, then the only way to do that is heat transfer and work, okay. We already talked about delta E system, which is nothing but your delta U plus delta KE plus delta PE. Now this delta U is essentially of the system. What about E in and E out? Now this is the transfer mechanism, Okay, this is the system information. This is this transfer mechanism. So what is coming in, what is coming out. It doesn't talk about the system. It's talk about what is going on at the boundary. So at the boundary, either the mass is entering, or the heat is being transferred, or the work is being done. So this gives you information of the heat, work, or mass. Okay, so we can write this in this form. So E in minus E out, you can take different contribution. This is due to the heat transfer, due to the work transfer, due to the mass flow. So you can also write in this form also, like Q in plus W in plus E mass A in as component E in minus Q out plus W out plus E mass out. Okay. This is equal to delta E system. So you can also do that. So it's the same expressions here. So this can be generalized in a very simple way, where we write E in minus E out, where this represent net energy transfer by heat, and that's the reason why this expression here was used, because this is a net heat transfer, this is a net work transfer, this is a net mass flow. So these are the different component of it. You can generalize it here and make it like net energy transfer by heat, work, and mass, and that should be equal to your change in internal energy, potential energy, that will be your delta E system. So you can also write in the rate form, that will be in the form of change in energy per unit time, and that's why this dot comes into the expression. Okay, so that will be E dot in minus E dot out equal to dE system by dt. Okay, so if the rate is constant, then you can find the change in the energy of the system by simply multiplying this rate by the specific time difference, and same with the heat, same with the work. You can also write the expression in unit mass by using a small e as an expression, and here it becomes E in minus E out and delta E system. You can use this unit mass basis in the form of a rate, that also you can do that. You can also write in differential form as done here. Now what about the closed system? When you undergo a process which is closed and as well as it's a cyclic process, which essentially means such that doing a process for a closed system such that you come back again to the same state. In such case, you know that energy is property, which is a point function. So delta E of the system should be 0 because it's coming back to the same state. So delta E should be 0 now, which means your E in should be E out should be equal to E out, right? So you can consider in this form, or you can write that delta E was your Q in minus Q out plus W in minus W out, and considering is a closed system, the mass term is not there. When this is 0, which essentially means Q net in should be W net out, okay, because the minus sign, if you take the second term here to the other side, it brings minus, so this becomes Q net in equal to Q net out, okay, that's why Q should be equal to W, okay. So that's for the closed and cyclic process. So let's take an example and then we will end this lecture. This is an example of a fluid which is cooled in a rigid tank while being stirred by a paddle. So the paddle wheel is here, okay, and the shaft work done is 100 kilojoule. Fluid loses 500 kilojoules of heat, and initially the internal energy of the system was 800 kilojoules. So we have to find the final internal energy. So what we are going to do? We are going to just apply the first law of thermodynamics here. Okay, so we can simply consider delta E. So delta E is your E in minus E out, and delta E is nothing but your delta U plus delta PE plus delta KE. So elevation is not changing and there is no change in the velocity. In fact, there is no velocity, it is a stationary system. So, these two terms should be 0. So, you have delta U as E in minus E out. So, what is E in here? It is nothing but shaft in, okay, and there is no heat supplied to the system. And what is E out? Is simply Q out. So, you have 100 minus 500. So, this is nothing but minus 400. So, this should be your U2 minus U1, which essentially means U2 should be 800 minus 400 kilojoules. Okay. So, this should be kilojoules here. So, that is 400 kilojoules. So, that is the answer for this based on first law of thermodynamics. Okay, so that will be the end of the lecture, and the next lecture we are going to talk about the conversion efficiency and its relevance for environment.